one thing at the time. So I will just stick to the lesson for
so now you're going to enjoy the ARIMA models. Okay, very good.
Yeah, better. I have a
Very
question.
good. So if you have
about
the SAN and ARMA models, you prefer the ARMA models. Okay, that's good.
Can I ask you something about the project?
Yeah.
Me and my mate, we managed to correct autocorrelation through Lex variable of the dependent variable, sorry, and dummy variables. But we decided which dummy variables, which year to select after having observed that we could use two legs of the dependent variable. Can we do it? Can we select the dummy variables after having re-estimated the model with two legs, or we have to decide which year to?
No, you can include the lags of the dependent variable, and then by looking at the residuals, you can identify what you want to include.
So the outliers.
Yes.
Okay, but so you confirm that we can look at the graph after we have re-estimated the model with the two legs.
You have to.
Okay.
You include the lags of the dependent variable, and then you can consider which dummies and how many dummies to include in the model.
Perfect. Thank you. And maybe a general question for everyone, because I think that you received some mails about permissions about the recordings of the lesson.
Yeah,
right?
I don't know how to make
upload
this
them
available to everybody. So I don't think I have access to it.
Okay, I think for sure it's a problem of permissions, because we can just see the first three lessons. The first three.
Yeah, but I don't know how to do. I don't know if I have the right to do it. So if you tell me how can I do it, then I will do it. But I don't know how to do it.
Do you mind if I ask you to show us your team's view, your team's desktop?
Let me.
The file section.
Yeah, okay. 1 minute. Okay, we're here.
Okay, 26.
So the recording is this one.
Okay. Open in browser.
I can only copy link. Open in browser.
The three dots on the left side. Yeah. No. Okay. Can you try to copy the link and send it in our chat?
Yeah, I've done this. Copy link. And this is what I have done. I have done this earlier.
Right. And we have to request access every time.
Okay. Can you see it now?
No, still we have to ask you for the access. But I mean, we will try. We will find a solution.
I have done this. Can you see? I have done this today.
Yeah. What I see is this thing here, and I will show you.
Can you show me what you can see?
Yeah, sure. Second.
Let me stop sharing.
Check in the chat. I've sent you a pic.
Let me go to OneDrive. Recordings. Okay. Yes, I don't know how to do it. Can you click on the link I just sent you, Salvatore?
Yeah, I'm trying. Recordings. Now, perfect. Perfect.
Recordings, can you see the recordings now?
Yes, every recording. Thank you. Yeah. All of them. Perfect.
Any other questions?
No, I'm fine. Thank you.
Any other questions? So Salvatore, now you can go to the beach.
Yeah, I will think about it.
Okay. Please send me a picture so I can have a look, because I missed Rimini seaside a lot. So let me remind you that yesterday we have done 3 models that belong to the time series family of models. We've done the autoregressive model. Who can help me? In the autoregressive models, what is the dependent variable? What is the independent variable? What is on the right-hand side? Who can remind me what is on the right-hand side in the autoregressive models?
Select values of dependent variable.
Okay, so we're going to have mu phi1 yt minus 1 plus the error term. In the moving average model, what is on the right-hand side? What is on the right-hand side of the moving average model?
Select values of error terms.
Of the error term, very good. And the ARMA model is a hybrid one, where we're going to have both an autoregressive component and a moving average component. Okay, so you can try to estimate different models, and how are you going to assess which is the right model? Which criteria are we going to use in order to select between alternative competing models? You're going to choose the best model out of all the different time series models you have estimated based on the information criteria. So in your project, you can include a table that reports all the information criteria from the different models. It's better if you report the Akaiki and the Schwarz criteria. Okay, and which model is the best? Which model is the best? The best model is the one that minimizes the information criteria. So minimizing the information criteria is what you're looking for. So the idea in this part of your project is to estimate alternative autoregressive and moving average models, save the Akaiki and the Schwarz criterion, and then choose the best one based on the information criteria. The best one can be used for forecasting. Remember that in this part of the project, the dependent variable is the growth rate of CO2 emissions. Okay, so I repeat one more time. In this part of the project, the dependent variable is the growth rate of CO2 emissions. The growth rate of CO2 emissions. Okay. Anything you want me to repeat? So a table with the Akaiki and the Schwarz from the different autoregression, moving average, and ARMA models could be inserted in this part of the project. Do you want me to repeat something?
Could you please repeat the test procedure in Gretel?
The test procedure.
Moving average model,
Okay.
AR model, and ARMA model. Could you please repeat the estimation procedure?
Can you see Gretel right now?
Yeah.
Okay. So this is the variable that we are interested in. Okay. This is the growth rate of CO2 emissions for the last 2 centuries. Okay.
I don't know if you're sharing your Gretel, but we can see it.
Okay, that's what I asked earlier. Can you see it right now?
Yeah.
Okay. So this is the growth rate of CO2 emissions. Okay. I'm going here, add log difference of selected variables. Okay. So let me create a time series plot. This is the growth rate of CO2 emissions for the last 2 centuries for the UK. We have more than 200 observations. Okay, so this is the dependent variable I'm interested in. So we're going to estimate an autoregressive one initially, then a moving average one, and then an ARMA 1. Okay, so my dependent variable is going to be the growth rate of CO2 emissions. I'm going to start with estimating a moving average model. So I'm going to have 0 here, 0 here, 1 here. I'm going to include a constant, and I'm not going to make any changes in the default options here in Gretel. So I can click OK. Ataul, can I click OK here?
Yes.
So this would be a moving average one model. This is the constant term nu. It is not significant. This is theta 1, and theta 1 is significant at the 1%. Okay, so this is the moving average one model. Now let me now go on and estimate an autoregressive one model. Again, my dependent variable is the growth rate of CO2 emissions. I would need an autoregressive one, and the moving average is going to be 0. Okay, so autoregressive one here, 0, moving average 1, moving average 0. Can I click OK, Taul?
Yes, you can.
Okay, so this is a moving average. Whoa, this is an autoregressive one. Okay, and the last model I'm going to estimate is a hybrid ARMA 1, which is going to have one autoregressive component, one moving average one component. Okay, so should be one here and one here. One autoregressive component, one moving average component, and then if you allow me, I'm going to click OK.
Can I ask you a question that what is the middle value 0? What is
The middle value is for variables that are not stationary.
Okay.
In my case, that's why I've asked you to run these models only for the growth rate of CO2 emissions, because the growth rate of CO2 emissions is a stationary variable. So given that this is a stationary variable, the middle value I, that stands for identification, is a stationary variable. And you should always leave it 0, given that the variable is stationary. Okay. Atul, can I click OK here?
Okay.
Okay, so let's have a look in all the models that I have. How did we say we can compare these 3 competing models? We can do it by looking at the archaic information criteria. In the case of this autoregressive model, the archaic is -500. This is moving average -498, and -498 in the case of pharma model. So which is the best model? The best model is the one that minimizes the archaic information criteria. Now, out of these 3, and there's no reason to do only 3, you can do more than 3, but I'm just showing you 3. Out of these 3, which is the best one?
Yeah, MA.
This one. In this case, we are minimizing the information criteria. Okay. What do you want me to repeat, Ataul?
No, it's fine. Thank you.
Any other questions?
No.
Other questions? You want me to repeat something? Now, if you run these models and you want to do diagnostics, the one you should do is only for autocorrelation. Okay, autocorrelation is the main test you can do in these time series models. Okay. Other questions? You want to repeat something? Salvatore, Theodore, any more questions?
I'm fine, thank you.
Okay, so you don't have any questions. Now, let me go to, and today we're going to talk about stationarity. Okay, you can see my slides, yes? I have also sent you the slides, correct?
Yes.
Okay. So, we're going to talk about stationarity today. And who is going to remind me what is the definition of stationarity we have used so far? What is the definition of stationarity we have used so far? Who is going to remind me? We defined stationary as a stationary variable as a variable that satisfies three conditions. What are these conditions? Who is going to remind me?
Mean variance and covariance of data series should be constant over time.
Okay, very good. So we need a constant mean, constant variance, constant covariance. Constant mean, constant variance, constant covariance. Okay. So these are the three properties that we have used so far when it comes to stationarity. Okay, these are the three properties we have used so far for stationarity. So the stationarity of a series can affect its behavior and its properties. For example, if you have a non-stationary process, shocks will be alive forever. If there is a shock, this shock is going to affect the series forever. Now, this is an important definition. Please highlight this. When we're regressing one non-stationary variable on another, then this regression is called spurious regression. If I repeat the definition one more time so you can make a note of this, when you regress one non-stationary variable on another non-stationary variable, when you regress one non-stationary variable on another non-stationary variable, this is called spurious regression. This is called spurious regression. Okay, this is called spurious regression. So if you have two variables that are trending over time, this is the definition of non-stationarity. This is the definition of non-stationarity. A regression of one on the other would have a high R squared, even if the two are totally unrelated. So a spurious regression is a regression that we think we have explained something. We think we have explained something, but we haven't explained anything because high R squared is coming from the fact that the variables are trending, does not imply any causality in the series. If the variable in the regression model are not stationary, then we can prove that the standard assumptions will not be valid. So the t ratios are not going to follow the t distribution. We cannot make hypothesis testing, etc. So when we have spurious regression, hypothesis testing is not valid. Hypothesis testing is not valid. Okay, so spurious regression, hypothesis testing is not valid. Hypothesis testing is not valid. Okay, so when we have two non-stationary variables, when we regress one on the other, this is the definition of non-stationarity. So here we have 1000 regressions of non-stationary variables that are independent variables. That means that if I regress one variable that is completely not related to another variable, what R² am I expecting to get? One more time, I'm regressing one variable to another variable that they are not, the two of them are not related. What value of R² am I expecting to get? What value of R² am I expecting to get when I regress one variable on another variable, assuming that the two are not related to each other? Assuming that the two are not related to each other.
Can you explain why it happens?
No.
So when we
my question,
regress,
my question, let me ask the question
sorry.
again. I have one variable and I regress it on another variable that the two of them are not related. What value of R² am I expecting to get? For instance, let me give you an example if you didn't understand this. I'm going to regress the advertising expenditure in Argentina on car sales in South Korea. Am I expecting advertising expenditure in Argentina to affect car sales in South Korea? Does it make sense?
No.
No. Okay, so what R² am I expecting to get?
A very high R² if the
Zero.
series
If the two are
such-
not related, I'm expecting an R² of 0.
Zero.
If they are not related, I'm expecting a very, very low R². Okay, now, if the two variables are non-stationary, here we have regressed 1000 regressions of two variables that are non-stationary and not related. I was hoping to get very low values, 0 values in all cases, but I'm getting 0 values only in 180 cases. I can see many cases where I'm getting high R², and this high R² is not coming from the fact that I have some type of causality. This is high R² is there because of the non-stationarity of the two variables, because the two variables trend over time. So what is the issue with non-stationarity? If I regress a non-stationary variable on another non-stationary variable, then I'm getting high values of R², when in fact I should get an R² of close to 0. Why I'm getting high R²? Because the two variables are trending over time. Okay, I should have got very, very low R², but I'm not getting. So if I get high R², I might think that I have some type of causal relationship. Okay, so if I get an R² of 75, I will say, okay, this is very good. I'm getting a very high R² value. But in fact, the R² value that I'm getting is not coming from the explanatory power of the regression. It's coming from the fact that the variables are non-stationary, that they trend over time. So, can I trust the value of R² when my variables are non-stationary?
No.
No. Okay, because they are going to be inflated. Okay, so I cannot trust it. I cannot trust the value of R squared. Okay. The same with the t ratio. Can I trust the t ratio when my variables are non-stationary? T ratio should follow the t distribution, and the t distribution should be distributed from, let's say, minus 2.5 to 2.5. Here, the t distribution takes values from minus 750 to 750. So both when I have spurious regression, when do I have a spurious regression? When I'm regressing one non-stationary variable on another, R squared cannot be trusted, T ratios cannot be trusted. Okay. So we're going to have two types of non-stationarity. One is what we call the random walk model. This is the random walk model. Okay. This is like an autoregressive model. This is like an autoregressive model, autoregressive one model, when in fact phi 1 equals to what? This is an autoregressive model where phi 1 equals to what? Who is going to help me? Sorry?
Maybe 1.
1, very good. So a random walk model is an autoregressive one with phi 1 equals to 1. And it tells me that today's value depends on a constant, on yesterday's value, and something random. Okay, and the second type of non-stationarity is what we call a deterministic trend with a deterministic trend process, where yt depends on a constant term, on a coefficient beta, and t is time trend. T is the time trend. Okay, now we're going to focus on the random walk for the time being. So, a more general case of the random walk is a model where phi 1 can take any value that we want. Obviously, we are going to concentrate on these two cases. We're going to concentrate on the case that phi equals 1. When phi equals 1, we have a random walk model. And we're going to also concentrate on phi being less than 1. Can phi be greater than 1? Yes. We call this process an explosive case. We're not going to talk too much about this case. We're not going to talk too much about the case that phi 1 can be greater than 1, because these are variables. When a variable has a phi 1 greater than 1, this is the case where a variable is increasing, has a growth rate that keeps on going up. Has a growth rate that keeps on going up. So this is what we usually, in economics, we call this a bubble. Okay, in economics, we call this a bubble. Okay, So we're going to concentrate on these two cases. So let me summarize here. When phi is less than 1, a variable is stationary. When phi equals 1, a variable is non-stationary and it's called random walk. When phi is greater than 1, the variable is non-stationary and we call it explosive case. Okay. Any questions? So, we're going to have three cases. The first case is phi is less than 1. If phi is less than 1, then the variable is stationary. When we say stationary, we mean that shocks to the variable eventually will die away. So things, when we say eventually die away, sometimes you forget. Okay. There is a process of forgetting. If there is a shock,
I have a question.
at some point you're going to forget what has happened. Okay. For example, the pandemic makes influences what is going to happen, but at some point this will die away. If phi
I have a
equals
question,
1,
sorry.
yes,
I'm sorry, I have a question. Okay, how many years do we have to expect the variable to die away? For example, 10 years is okay, or 100 years? How many
Okay,
times?
this is
How
a very
much
good,
time?
it's a very good question. This depends on phi. Okay, so one way of measuring exactly what you said is what we call half-life. And there are measures of half-life depending on phi. So if phi is 0.95, that means you are forgetting very slowly. If phi is 0.1, that means you are forgetting very rapidly. So the speed with which you are forgetting depends on how close to 1 phi is. If phi is close to 1, the process of forgetting is very slow. If phi is close to 0, the process of forgetting is very slow. So let me give you an example. Economic variables forget very, very difficult. So the way that macroeconomic variables forget is very, very slow. So macroeconomic variables have a phi, let's say, 0.9. So unemployment, for example, forgets very, very slowly. So if there's a shock in unemployment, you need time to absorb the shock. If there is a shock in GDP, you need some time to absorb it. If there is a shock in CO2 emissions, you might need some time to absorb it. Financial variables, on the other hand, they do forget very easily. So they absorb shocks much easier. So if there is a shock in the stock market, in 2 weeks' time, maybe the shock would be absorbed. In 2 weeks' time, the shock would be absorbed.
Thank you.
Okay, so depending on the value of phi, you can measure how quickly or how slowly a shock can be absorbed by the system. Okay, if phi equals 1, a shock is going to persist forever. This is a variable that is non-stationary. And we call this specific case, we call it random walk. This specific case, we call it random walk. Okay.
Can you make an example of a variable that is non-stationary forever with a random walk? Can you
Yes,
make
I'm gonna show you in great later on. CO2 emissions at GDP are non-stationary. The growth rate of CO2 emissions is stationary. I'm gonna show you in a minute. And case number 3, which is something that we don't have it in economics that frequently, is what we call an explosive case, where phi1 is greater than 1. Okay. Now, how do we remove the trend if a variable is non-stationary? How do we make it stationary? If the variable is non-stationary, how can I make it stationary? How do I make it stationary? If the variable is of this, if the variable has non-stationarity of this form, if it is random walk, then what we do is we take first differences. So if a variable is a random walk non-stationary, how do I make it stationary? By taking first differences. One more time. If I have a variable that is non-stationary, how do I make it stationary? Answer, by taking first differences. So here, when we say first differences, we imply that the variable is locked. Okay, we imply that the variable is locked. So let me give you an example of a variable that is non-stationary and how we can make it stationary. Okay, so here we have GDP per capita. Okay, does this variable have a constant mean? Does this variable have a constant mean? Does this variable fluctuates around a constant mean?
No.
No. So what I have done is I have taken the first logarithmic cases of GDP. So this variable here is the growth rate of GDP. Okay. Does this variable have a constant mean?
Yes.
Does this variable have a constant mean? So this variable is non-stationary. You can see it trends over time. It keeps on going up. And this variable here is stationary. Why? You can see it fluctuates around the constant mean. It crosses. One way of looking at stationarity is the fact that this variable crosses the mean very, very frequently. The mean is 0. You can see how frequently this variable is crossing the mean. Okay, you can see how frequently this variable is crossing the mean. Okay, so this is an example of a non-stationary variable. How did I make it stationary? How did I transform this non-stationary variable into a stationary variable? What I did, I took logarithmic first differences. And the logarithmic first differences is a stationary process. Okay. Are we okay?
Can you demonstrate why the logarithmic form is a stationary process? Sorry.
So far,
So
we we have seen the definition of non-stationarity, which we talked about two days ago. It has a constant mean. So the constant mean, we're going to do the proper test later on, but the constant mean, you can see it by the fact that it crosses the zero. Can you see the zero line here?
Yeah, of course.
Yeah, it crosses zero very frequently. This variable here, can you imagine any constant variable that would cross it frequently? No, because the variable keeps on going up. So if a variable keeps on going up, it's non-stationary. If a variable fluctuates around the constant mean, it's stationary. Okay.
Okay, thanks.
Okay. So let's see some examples of processes. Now, this is a white noise process. When we say white noise process, who is going to remind me? When we say white noise process, what do we mean? When we say white noise process, what do we mean? What type of processes are characterized by
Zero
this
average,
white
average, and almost elasticity.
A white noise process is a process that is completely what? A white noise is a process that is random. Okay, there is no structure. Okay, is a white noise a stationary or non-stationary variable? What do you see in front of you, stationary or non-stationary?
Stationary.
It's stationary. You can see that it fluctuates around zero. Okay. And it also has a constant variance. You can see that the variance between -2 and 2, all the variability that you observe is between -2 and 2. Okay. Now, are these processes stationary or non-stationary? Can you see a clear trend in these two variables?
Yes.
So are they stationary or non-stationary, these two variables?
I would say non-stationary.
How can we make them stationary if we want to employ them in a regression analysis? How can we make them stationary? What should I do to these variables in order to use them in a regression?
Taking the logs.
We need to take not only logs, we need to log them and
to use the growth rate.
First differences, sorry.
We should use first logarithmic differences. Okay, so if you want to make them stationary, take first difference of the logs. So log them and then takes first differences. Okay. So if you have a non-stationary variable, we take the logs and then you take the first difference and you make it stationary. Okay. I'm going to skip. So this is the average temperature anomaly from 1850 to 2018. Does this is stationary or non-stationary process? Is the station? Yeah, there is a up to
Stationary.
this point it looked stationary, but after this point you can see there is a trend. Okay, so what we are observing here is what in the people in the literature are called the greenhouse effect. Okay, so when you want to examine, to test the greenhouse effect, what you're looking really is testing the average temperature anomaly stationarity properties.
Sorry,
Okay.
Professor, can I ask you something?
Yes.
This topic on stationary be checked together with parameters stability test that you showed us the other day? The CHO test, the COSUM test.
Yes.
Are they somehow related?
Yes, I'm going to show you in a minute. I'm going to show you the test, and then I will get back to these points. Okay.
Okay, thank you.
So this is the temperature anomaly in the northern hemisphere. You can see that up to here, it looks like there are deviations around the constant mean. After this point, you can see a clear upward trend. Okay, again, this is the greenhouse effect. Okay, so do you want to have a break, or do you want me to continue and we have a break later on?
I would like to have a break, actually.
Okay, let's have a 15 minutes break, and then we're going to be back. 15 minutes. Back at 5:10. Okay, 5:15. Can you hear me again? Can you hear me again? 1, 2, 3. Yes.
We can hear you. We can hear you.
Okay, so you can hear me. So, if we have this process, which is a random walk process, by taking first differences, we're going to remove the non-stationarity. This case is called, we can generalize this concept to consider the case where the case considers more than one unit root. Now, this unit root refers to the characteristic root we talked about 2 days ago. Okay, so we can generalize this and say, and we are going to call a series I0 integrated of order 0 when a variable is stationary, and we're going to call a variable I1 when I need to take differences one time in order to make it stationary. So in our example, GTP is an I1 variable, and the growth rate of GDP is an I0 variable. Okay, CO2 emissions is an I1 variable. The growth rate of CO2 emission is an I0 variable. So when we say a variable is I0 integrated of order 0, we mean that this variable is stationary and can be used in a regression. So I0 variables can be used in a regression. I1 variables cannot be used in a regression. Okay, I0 is a variable that is stationary and can be used in a regression. I1 is a variable that is non-stationary and cannot be used in a regression. Okay, so I0, one more time, is a variable that's stationary. I can use it in a regression. I1 is non-stationary. I cannot use it in a regression. What can I do in order to make an I1 variable? What can I do in order to make an I1 variable stationary? I can take first differences. Take first difference of the logs. Okay, take first difference of the logs. This is exactly what we did in the process, in the project. Okay, this is exactly what we did in the project. This is exactly what we did in the project. Okay, so a variable can contain 1, 2 unit roots. The majority of the variables you're going to employ are I0 or I1. There are also a very small minority of variables that I2 variable. To make it stationary, you need to take differences. You need to take differences twice. Okay. Now let's see how we can test for a unit root. So this is an autoregressive one process, and you want to test whether the series contains a unit root or not. So the null hypothesis in words is that the series contains a unit root. This is usually denoted as phi equals 1. Or in other words, the null hypothesis says that the variable is not stationary. The variable is not stationary. Okay, the variable is not stationary. The alternative is the series is stationary, phi is less than 1. Okay. So one more time, how do we test for a unit root? We need an autoregressive one model, and we can test whether the series contains a unit root. In other words, whether the series is not stationary against the alternative that is stationary. Now, what's the problem with this autoregressive one model? This could be a spurious regression. If this is a spurious regression, if this is a spurious regression, then can I do hypothesis testing?
No.
No, okay. So how can we solve this issue? Well, Darwin and Watson said instead of estimating this model, estimate this. So this is called the empirical the empirical Dickey-Fuller. Okay, this is called the empirical Dickey-Fuller, and this is the one we're going to estimate. So the null hypothesis in terms of the empirical Dickey-Fuller is psi equals 0, and in terms of the alternative is psi is less than 0. Okay, so one more time, what is the null hypothesis? The null hypothesis says the series contains unit root. In terms of the theoretical Dickey-Fuller, this is the theoretical Dickey-Fuller. It's phi equals 1. In terms of the empirical, it's psi equals 0. If you want to say it in words, the null hypothesis says that the variable is not stationary. Okay. Remember that only stationary variables can be used in a regression. Only stationary variables can be used in a regression. Only stationary variables can be used in a regression. Okay, so one more time. We have the theoretical Dickey-Fuller and the empirical Dickey-Fuller. What's the null hypothesis? Series contains unit root, phi equals 1, psi equals 0. Okay, and the variable is not stationary. Okay. Okay. One more time. Phi equals 1, psi equals 0. The variable is not stationary. The alternative, the series is stationary. The series can be used in a regression. Phi is less than 1, psi is less than 0. Okay. Now we have at least 3 alternatives of the Dickey-Fuller regression. The last one, this is the theoretical Dickey-Fuller. that contains a constant term and a trend. The empirical one, I'm going to write it here, is delta yt mu, the constant term, lambda times the time trend, plus phi, sorry, this is the empirical one, so it's psi yt minus 1 plus ut. Okay, and what we're interested in is this psi. So we need the t statistic psi divided by the standard error of this psi. Psi divided by the standard error of this psi. Okay. So this is the important bit, the standard error, and this will tell me whether to reject or not reject the null. So this test statistic will tell me whether I can reject the null. And what does the null says? The null says psi equals 0, no stationary process. Okay. Any questions? Okay. Now, these are the critical values, but you don't need to worry about this because Gretel will give you the p-values directly. Okay. And the last but very important thing is sometimes Dickey-Fuller regressions suffer from autocorrelation. How do we solve the autocorrelation issue if autocorrelation is present? By adding lags. Okay, so for example, an augmented Dickey-Fuller 1 model is a model where I'm going to insert one lag in order to remove possible autocorrelation. So I'm going to have delta yt equals mu plus lambda plus psi yt minus 1 plus alpha 1 delta yt minus 1 plus ut. Okay, now this is the error term, obviously. This is the error term. Why I'm adding this term? To remove autocorrelation. Psi is what I'm interested in. This is the trend. This is the constant. Okay. So the null hypothesis is always psi equals 0, which implies non-stationarity. Any questions so far? Any questions? Now let's see how we can test for a unit root in our data. Okay, let me show you the graphs so you can see the difference between a stationary and a non-stationary process. So I have CO2 emissions and I have CO2 emissions and the growth rate of CO2 emissions. Okay, this one, or let me do it with GDP. So GDP is non-stationary, as you can see. The growth rate of GDP is stationary. Okay. Can you see this? Yes. Can you see this?
Yes.
Yes, we can.
Okay. So let me check GDP per capita for stationarity. So you need to go to the option variable, and then you can click on ADF. You can click on ADF. Okay. So here we are going to, Gretel is asking how many lags do you want to consider, and based on which criteria you're going to choose the lags. Okay, so here I can choose either the Kaiki or the Schwarz criteria, and the maximum number of lags that Gretel considers is 14. Okay, the maximum lag that Gretel considers is 14. Okay, now we are asking Gretel to consider a Digifuller with constant and a Digifuller with a constant and a trend. Use the level of the variable, and let me click here, show regression results, so you can see the regression results that we have available. Okay, let's see where the results are coming from, which is the regression results that can produce the Digifuller. Okay, any questions? Can I click OK? So if I click OK, look the results. So Gretel is running 15 regressions with no lags, with one lag, with two lags, etc. It saves all the Akaiki information criteria and chooses the model with the lowest Akaiki criteria. Which is the model with the lowest Akaiki criteria? Which is the model that minimizes the Akaiki information criteria? How many lags minimize the Akaiki information criteria? Is it this one, the lowest Akaiki? Do you agree?
Yes.
Okay, so this is the lowest information criteria, so you can see the results here. Okay, let me go here. So this is the model I wrote. It's similar to the one we have estimated. Okay, so mu is the constant term, is this constant term. This model does not have a trend. Is the constant term statistically significant? Is the constant term statistically significant?
No.
No, it's not statistically significant. This is, which coefficient is this one? based on the model, which is this coefficient.
Phi.
This is psi. Phi
Psi.
is it's the theoretical model, and we usually don't estimate this. Okay, and this is which coefficient is this one? This is alpha 1. Okay, now the null hypothesis is that the series contains a unit root and the p-value is 1. So the null hypothesis that the variable is non-stationary, the null hypothesis says that the variable is non-stationary. The null hypothesis says that the variable is non-stationary. What do I do with the null hypothesis? Can I reject it? The p-value of the null hypothesis of non-stationarity is 1. Is the null hypothesis a likely hypothesis? Is a null hypothesis a likely hypothesis? Can I reject the null?
No, you cannot.
No. So the variable is what? The variable is
Non-stationary.
it's non-stationary, exactly as I saw it on the graph. Okay, so this Dickey-Fuller says that this variable here is non-stationary. If I do the same thing with the lambda, this is the model with lambda. Lambda is this variable here. Again, Gretel is running 15 regression. It chooses the one that minimizes it minimizes the archaic information criteria. So we have one lag. The null hypothesis is that the variable is not the variable is non-stationary. Okay. So this is the constant term mu. This is psi. This is alpha 1, and this is lambda. Okay, this is what I'm interested in. And the p-value is 99%. So again, I cannot reject the null. Again, I cannot reject the null. Okay, I cannot reject the null. Any questions? So let me now do the same test for the growth rates. What I'm expecting to find for the growth rate of GDP, I'm expecting to find that the variable is stationary. Okay. So I would go to variable again, augmented Dickey-Fuller, and then I would click OK. Okay. Sorry, I have to choose this variable and then do Dickey-Fuller test. Okay. So I would click OK, which is how many lags minimize the archaic information criterion? How many lags minimize the archaic information criterion?
14.
But it has a minus in front. So you're looking for the most
6.
negative one.
5 maybe.
6. Okay. So we have a model with 6 lags. Can you see 1, 2, 3, 4, 5, 6? Okay. This is what I'm interested in. What's the p-value of the Tiki Fuller? The p-value of the Tiki Fuller is 0.60 and then 1. So the p-value is basically 0. Okay. So the null hypothesis is non-stationarity. What do I do to the null hypothesis? What can I say about the null hypothesis given that the p-value is 0?
We reject the non-stationary.
We reject the null hypothesis of non-stationarity and we conclude that the variable is stationary. Okay, so this is the null hypothesis.
And so, Professor, as it is very close to 0, we can say that GDP changes very slowly through time?
No, it's stationary. So it's stationary, so we can say that the shock will be absorbed at some point in time.
Okay,
Okay,
thank you.
shock will be absorbed at some point in time, whereas the GDP is non-stationary. If we include the time trend, again, we are finding the same conclusion. The p-value is 0. So we have done Tiki Fuller in the GDP and found GDP to be non-stationary. We have done growth rates of GDP. We have done a unit root test on the growth rate of GDP, and we have found that this is stationary. Okay. Now a difficult question. Initially, in the project, let me show you where we want this analysis. This analysis is this one. So you can do an autoregressive model, a moving average model, and unit root tests. Unit root tests in all your variables. Okay. So we have basically covered all the steps of your project. We have basically covered all the steps of your project. We have done autoregressive models, we have done moving average models, and today we have done the unit root test. Okay. So in the first part of the model, I have run a regression on CO2 emissions and GDP. Given that both CO2 emissions and GDP per capita are behaving like this, who is going to tell me this regression that we have run in the first steps of the model, how it's called, what type of regression this is?
Linear.
How we would call this regression?
Spurious.
This is a spurious regression. Very good. Why it's a spurious regression? Because I have shown that this variable is non-stationary. Correct? It's clear that it's non-stationary. and maybe this one is non-stationary. I don't know, but I have to check. If both of them are non-stationary, then the first regression you have run is a spurious regression. Okay, let me check CO2 emissions per capita and see what the Dickey Fuller will tell me. Okay, can I click OK? So, as I said, the p-value is 57%. So this is also non-stationary. Okay, so both CO2 emissions per capita and GDP per capita are non-stationary. So at this point in time in the project, I can write that this model is spurious. Okay, and if you have the same results, I repeat, if you have the same results, then you can say that the model that is more appropriate is the model that uses only stationary variables. I repeat, this is the results I find. You don't need to find the same results. So based on the analysis we have done, which is this is a spurious regression, but this is a model that is using stationary variables. So I can rely on this model without any problem. Okay. Questions?
Can I ask you?
Yes, whatever you want. Is this Theodore?
Simone,
Simone, I'm hearing Simone.
so basically the GDP and the CO2 emissions are integrated of order 1?
In our case, well, in my case, because I'm doing the UK, yes, they are both integrated of order 1. So the first regression is a spurious regression, and the first difference regression is not spurious.
Okay, thank you. And how can we see if they are integrated of order 1 or of more order?
That's a good question. Okay. I've done, you can see these two variables here, yes?
Yes, yes.
Well, I go here and check whether these are stationary. This is for the CO2 emissions, and I'm going to do the same for GDP per capita. You can see yeah, this is a marginal case. 17. Sorry. Oh, sorry. GDP per capita is stationary when I take the first differences. CO2 emissions is not. You can see CO2 emissions is not. It's not stationary. Okay.
Yes, thank you.
Now, I will show you some other tests for unit root that are available. You can see them from here. that I will talk about after the break. Any questions? So how do we decide how many lags we're going to use in the augmented Dickey-Fuller? We're going to use information criteria, either Akaiki or Schwarz, to do it as Gretel is doing this automatically. Let me repeat that we are taking the lags to correct for autocorrelation. To correct for autocorrelation. Okay. Any questions? Any questions? You want to repeat something? You want to repeat something? Is it clear what you need to do for your project? No? Okay, if there are no questions, let's have a break.
Sorry, I lost a passage.
Sorry?
I lost a thing. Can I do a question, please?
Yeah.
Yeah. About the last test you did with the variable.
Yeah.
Yeah. We see a series of number. And
So,
can you explain the
one?
meaning? Okay. Can you do the variable? Okay. Can you do
Okay,
it,
now
please?
I have used the growth rate of GDP. I
Okay.
have highlighted the variable growth rate of
Yes.
GDP. This is variable number 9.
Mhm.
I'm going to the option variable, unit root test, and then Dickey-Fuller.
Okay. And then in the output of the test, we see.
Then here, the only thing I have chosen is click on show regression results. All the other are the default options.
Okay.
And
Okay.
from
Can you
here,
explain again, please, the meaning of minus AIC, all of that numbers?
this is the Akaiki information criteria we talked about yesterday.
Yeah.
Okay,
Yeah.
so
I know.
Gretel is estimating 15 regressions, and from each regression it saves the Akaiki information criteria. So this is a regression with 14 lags, and this is the Akaiki information criteria. This is the regression with 13 lags, and this is the information criteria. So out of this, Gretel automatically would tell you which is the model with the lowest Akaiki. In this case, the model that minimizes the Akaiki information criteria is with 6 lags. Okay, that's why here you see
Okay, just
1
6 lags.
lag,
Okay.
2 lags, 3 lags, 6 lags.
Okay.
Now, here we are interested in this null hypothesis that the series contains a unit root. In other words, the null hypothesis is that the variable is non-stationary. Okay. And you need this line, and you also need the p-value. The p-value here is virtually 0. Okay, so if the p-value of a hypothesis is 0, that means that I can reject the null hypothesis.
Okay, thank you.
So in this case, I reject the null and conclude that the variable is stationary.
Okay,
So
okay, perfect.
I can use it in a regression.
Oh, thank you for repeating everything. Now it's more clear. Thank you.
Okay. Other questions? Oh, Marcus said for the project you have to show. Well, you don't have to show, you have to test. Okay. If CO2 emissions per capita are not stationary, this is evidence in favor of the greenhouse effects. I'm answering the question by Marco now. If, I repeat, CO2 emissions the growth rate of CO2 emissions per capita are not stationary, this is evidence in favor of the greenhouse effect hypothesis. That means that emissions keep on going up, keep on increasing. Okay, Marco? So you have to test for stationarity, GDP per capita, CO2 emissions per capita, the growth rate of GDP per capita, and the growth rate of CO2 emissions per capita. Okay. Marco, is this okay? Okay. So let's have a break for 15 minutes. We're going to be back at 5. We are back. Okay. If you have any questions about the coursework, please let me know so I can repeat everything. Okay. Okay, let's have a 15 minutes break. I'll see you at 6:15. Hello, can you hear me again? Can you hear me? One, two, three.
Yes. Yes.
Okay, so do you want to repeat something?
Professor, can I ask something about the project?
Yes.
When in the first section, when you say figures for the data and summary statistics, are there specific figures we should include? Or does that just mean like residual plots over time?
The residual plots should go to the analysis, which this is the data you're referring to.
Yes.
Is this, yeah, this is figures for the levels and the first differences. So residuals should go under 3. In number 2, you should do this type of figures.
Okay.
I think we talked about this a couple of days ago. Let me this type of figures, and you can do figures like time series plots, scatter plots, and also I think I show you how to do the color XY plot.
Okay. Thank you.
Okay. Other questions? Let me see if I can plot everything together. Okay. Other questions about the project? You want me to repeat something? Okay. Testing for higher order integration. This is something you should do when a variable is not I1, when I2 could be the case, when a variable could be I2. When a variable could be I2. So in this case, you need to take first difference again, and then redo a Dickey-Fuller test. Okay. Now, Dickey-Fuller is not the only unit root test. There are other unit root tests. One option is the Phillips-Perron test. The Phillips-Perron is a test that is similar to the Dickey-Fuller, but the correction for autocorrelation is different. What does the Dickey-Fuller does for autocorrelation? It adds lags. Okay, Phillips-Perron is using a non-parametric correction to autocorrelation. Let me show you how we can do the Phillips-Perron. The Phillips-Heron test is available from here. Unit root tests, Phillips-Heron. Is it available in your Gretel? Is it available in your Gretel?
Not in mine. Maybe it's a external.
Okay, so if it's not, Salvatore, is it you?
No, it's me, Theodore.
Theodore, okay. So if it's not available, you go to the option File, Function Packages on Server. Okay. And here, try to find the Phillips-Heron. If you do it alphabetically, it's this one. Okay, you right-click and install it. If you install it, you're gonna get the Phillips-Heron also in your Gretel.
Okay, thank you. Now I have it.
Okay. So once you install it, you go to variable, unit root tests, and you have Phillips-Heron here. So which variable you want to test? You want to test the growth rate of GDP. You need to put a constant or a trend. I'm going to put only a constant. 0, you leave 0 here as the automatic correction for autocorrelation, and then the only thing you need to click here is OK. Can I click OK? Can I click OK? OK. Now the p-value you can see is 0. Okay, the p-value is 0. So the null hypothesis says that GDP, the growth rate of GDP is non-stationary. The p-value is 0. So what I do to the null hypothesis, when the p-value is 0, what I do to the null hypothesis?
We reject the null hypothesis.
I reject the null hypothesis. I reject the null hypothesis. Okay. So can you do this test as well in your project? You can do the Dickey-Fuller and the Phillips-Heron. Okay, let me see CO2 emissions also. Variable, unit root, Phillips-Heron. CO2 emissions, constant 0. You can see Phillips-Heron says that CO2 emissions per capita are stationary because the p-value is 0. Okay. Anything you want me to repeat here with the Phillips-Heron? I repeat, if you don't have the Phillips-Heron, You can install it from here. Okay. Now, the problem with like Dickey-Fuller tests and Phillips-Perron tests is when phi is very close to 0, they tend to not behave properly. So when phi is less than 0 but close to it, then it tends, these tests are not behaving properly. So what we could do in this case is employ stationarity tests. So please make a note that Dickey-Fuller and Phillips-Perron, they are unit root tests. There are also stationarity tests, and the basic stationarity test is called SPSS. Now, KPSS, not SPSS. The stationarity test, they have the null hypothesis is exactly the opposite compared to the Dickey-Fuller. It's exactly the opposite compared to the Dickey-Fuller. So the null hypothesis is the variable is stationary, the alternative is non-stationary. Okay. This test is called KPSS. So in order to compare, we need this table. This table is very important. You can also reproduce it in your project. So Dickey-Fuller and Phillips-Perron, they have the null hypothesis that the variable is non-stationary. KPSS has the null hypothesis that it is stationary. So if we have a variable that is stationary, we need the Dickey-Fuller to reject it and KPSS not to reject it. This is going to confirm that the variable is stationary. Okay. This is going to confirm that the variable is stationary. Can I show you how we can do this? Can I show you how you can do this? Okay. So I'm here and I'm going to do a Dickey-Fuller for the growth rate of GDP per capita. Okay. The growth rate of GDP per capita. So variable unit root test, augmented Dickey-Fuller. Okay. So this is Dickey-Fuller. The p-value is 0. So I reject the null. Are we okay? I'm going to do exactly the same with the KPSS. Phillips-Perron. GDP growth rate of GDP per capita. P-value is 0. I reject the null. So both the Dickey-Fuller and the Phillips-Perron have rejected the null. Okay. Now I'm going to do the same thing with the KPSS test. The KPSS test is not a unit root test, is a stationarity test. Is not a unit root test, is a stationarity test. Okay. So unit root test, KPSS test, lag order of KPSS, and I'm going to keep the default here, and I'm going to click OK. So the p-value is 6%. So at the 10%, at the 1%, I cannot reject the null. Okay. At the 1%, I cannot reject the null. So question, do I need all the unit root and stationary tests to agree? No. I don't need all of them to agree. The important thing in the project is to report them. You don't need to make all these tests to make them all. There's no point in having all of them. Agree. The important thing is to demonstrate that you know all of these tests. To demonstrate that you know how to use all these tests. Okay. What do you want me to repeat here? What do you want me to repeat? Okay, so for your project, you can do the Dickey-Fuller, you can do the Phillips-Perron, and the KPSS. Okay. Now, there are also unit roots with breaks. So when we talked about breaks, how did we account for breaks in the past? When there is an outlier, how do we account for breaks? What did we say earlier? When you have an outlier, how do we account for this outlier?
With dummy variables?
With dummy variables. So the standard Dickey-Fuller unit root test cannot perform well when there is a structural break. So what people are doing is they include a structural break in the unit root test. So when we say they include a structural break, they introduce a dummy variable. And this dummy variable can capture this structural break. Okay. Now, this structural break, obviously, you need to be able to identify when the break is taking place. Okay. So the basic model by Perron, for example, says that the dummy variable takes the value of 0 before a specific event, before an event, and it takes the value of 1 after an event. Okay, so for instance, you might have something like this. Okay, this break, you can capture it with a dummy. Okay, the problem is how can we identify this, this event? So this Perron test looks exactly like a Dickey-Fuller. This is a psi for the Dickey-Fuller. This is a constant term. This here is to correct for autocorrelation. And this dummy, either this or this, is for capturing for capturing the break. This is for capturing the break. Okay. Now, how do we find the break? Well, usually we're going to employ models like Zivot-Andrews or Banerjee models, where they are looking for all potential breaks using recursive or rolling estimation to find the break. Okay, now I'm going to show you how you can do this in Gretel. I'm going to show you how you can do this in Gretel. Okay, so there is no Phillips-Perron test in the menu, so you need to go to the server to look for it. Okay, so you go here and search for a type of or if you go here and do okay, this is not responding. Okay, let me go to let me go to K. Okay, you need to go here to K and install this test. It's called Capetanius test. Okay, this is called the Capetanius test. If you install it, if you install this, then I can close this. I can go to File, Function Packages, Local Machine, and the test would be available here. I'm going to the test and double click, and then I can click execute. So let me go to the growth rate of CO2 emissions, and this test allows me to identify breaks. This test allows me to identify breaks. Okay, so the maximum number of breaks is 3, the lags is 1, and the only thing I can do after that is click OK. Okay, I have chosen the growth rate of CO2 emissions to to test for brakes once I allow for once I allow for brakes to take place. Okay, can I click OK? Are you following me? Can you do the same thing? Theodore, you follow me?
Yes, yes, I'm at the same point like you, yes.
So I can click OK, yes?
Yes, yes.
Okay, now you can see this is running. So this is the test statistic, in this case is minus 15. You can see this is in absolute terms bigger than the critical values. The test has identified 3 brakes, one in 1823, one in 1926, and one in 1903. So this is a very useful test because it allows me to identify the brakes. It allows me to identify the brakes by looking at all potential brakes. So these are the 3 tests that the test has identified. Okay, and here you can see a Dickey-Fuller type of regression with the brakes. So the null hypothesis is still the variables are non-stationary. Given the test statistic, my conclusion is that the variable is stationary once I allow for structural brakes. 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 Any questions? So
Professor,
what are the advantages of this process? There are 2 advantages here. First advantage is we identify brakes. We consider all possible brakes, and the test finds the brakes on its own. Okay, so 1823, 1926, 1903. You can see the dates here. And then once the test finds the brake, we're using the brake in the brakes in the Dickey-Fuller test, and then we recalculate the test statistic once we allow for these brakes to operate. Sorry, Antoine, you wanted to ask something. Sorry for interrupting you.
No problem. I am asking you that if the test statistic is lower than the critical value, then will be any problem?
Yes. If the test statistic here is minus 15, if the test statistic was minus 2, we would say that the variable is not stationary.
Okay.
If it was minus 2, it would be non-stationary. Now it's minus 15, it's stationary. Other questions? Do you want me to repeat this one or you can do it? Do you want me to repeat something here or you're okay?
Sorry, Professor, but the brakes are to be considered like our dummy variables when we re-estimate the model?
These are the brakes that this test identifies. Okay, if you are talking about the breaks you have identified in your first stages, these are identified through the residuals. So if your question is whether these dummies and the dummies you have done, you have considered initially should be the same, the answer is no. The dummies you consider initially were dummies coming from a regression of two variables. Here, these are dummies from only one variable, not two. Okay. Now, if you want to run this test easier, I go to Tools, Command Log. This is everything I have done so far today. If I copy this and go to console, I can basically rerun the test by copying the function and pressing enter. Okay, so in console, I have the same. Okay, now I can go and paste it again, and obviously I can go here, I can delete O2, and I can type GDP per capita instead. Okay, so the name I have here is the same as the variable. And I can click enter to get the same test for GDP per capita. Theodore, can I click OK?
Yes, yes.
So for GDP per capita, you can see the test statistics is -14. These are the 3 breaks, and it looks like once I allow for breaks to take place in the model, they are also stationary. The growth rate of GDP is also stationary. I'm listening to questions. Do you want to repeat something, Gretel? Do you want me to repeat something, Gretel? Can you show how to copy it in the console? Yeah, I'm going to command log. The command log is the series of all the commands I have employed in the past. So you can take this one or whatever you want. Highlight, right click, copy, go to console. Console is from here. And you can paste it. Control V. And then press enter. Okay. Any questions? Anything you want me to repeat? anything you want me to repeat? Any questions about your project you want me to?
Yeah, if it's the right time, I have a question about our project, but I don't know if
Please.
go?
Yes, please.
So, when we run the univariate time series model, we are using a Mac computer. If we don't check the box saying X12 greater, our application just crashes. If you can go to the yes.
So you want to do autoregressive?
Yes.
Here.
Exactly. Yes. We have yes, this one.
And you do this for the growth rate of CO2 emissions, nothing else.
Okay,
Only the
yes.
growth rate of CO2, nothing else.
Perfect. The problem is that if we don't check the box use X12 ARIMA.
You share your screen so I can have a look.
It's my partner's screen, so I cannot actually.
Okay.
But you were there actually.
Okay, okay, so I repeat, you need.
If we check the box use X12 ARIMA, the Gretel app crashes and we don't understand why.
So let me go back. Okay, I repeat here, you need the growth rate of CO2 emissions, nothing else. Okay, and here the regressors, nothing. And here you put autoregressive 1, moving average 1. This should be 0, include the constant, that's it.
Yes, we do exactly like this, but
yes,
we don't
Prof.
understand.
Yes, if I do this, my app close itself, and then I can go ahead. If I click on use X12 ARIMA, otherwise it do the test, but I don't understand why.
Yeah, do you have the last version of Gretel?
Yes, I downloaded this morning again. This is the last version.
And you have a Mac as well?
Yes.
Yeah. Can you
I follow
Can you download the Windows version and use the parallel option in Mac and run it in under Windows?
I can try it. Okay.
Yeah.
Okay, thank you.
Thank you.
Yeah, I don't know why this crashes on Mac. Other questions? Is everybody ready for the presentations next week? Okay. Other questions? If there are no questions, then I think we should have some rest, and then we're gonna meet tomorrow. Okay. If there are no questions, I would say have some rest, and we're going to meet tomorrow again. Okay. So good night to everybody. Thank you, Marco. Have some rest. Bye-bye to everybody.